So we are slightly behind schedule, but we started late. Next speaker is Greg Hager. Greg will speak about vision as well. Greg is professor at Johns Hopkins, and he's also assistant director at NSF for computer science and engineering.
Great. Thank you, Raja. And it's really a pleasure to be able to be here today to speak with you. Yeah, as Raja suggested, I'm going to speak about vision. In fact, a lot of what I'm going to talk about is very similar to what Dieter talked about. So I decided, among other things, I liked his title better. So I'm going to steal his title and say, Robot GBT, are we there yet? And the picture on the right, just you know, is generated obviously by generative AI. And it was really the title that I put in and said, make a picture for me. So I'll return to that in a minute, too. But I wanted to go back to 2000. So this is literally a slide from a talk I gave back then, where I was talking about vision-based control and talking about the state of where we were. And the reason for this slide, the hook for it, was that I had a workshop in the basement. I did a lot of woodworking at the time, and I had my son, who was probably 5 or 6 at the time, who could help me out. And I said, by the time he finishes high school and leaves the house, I need a robot that can take his place. So we've got about 10 or 15 years to get a robot that's good enough to manipulate tools and have all the properties of a good workbench assistant. So the way that the paper laid out is I really was talking about how do you program robots to do general vision-based control. And this is literally a slice of code from that paper. And the key thing here was I was basically saying, look, there's a bunch of things we already know how to do in computer vision. We can do real-time tracking. We can do control based on that. We know how to compose that together to solve interestingly complex tasks. The real problem is we just don't know how to ground it efficiently in the real world. So in some sense, all the stuff in black on this slide we knew how to do. All the stuff in red were the things that we didn't know how to do, like find the screwdriver that you actually wanted to work with, or find the tip of the screwdriver so you could put it on a screw. But the thing I'll point out is what was nice about this sort of representation of a task is, it has all the great properties of programming that we've all taught to enjoy. It's composable, it's debuggable, it's interpretable, you can read it, and it's easy to test and get to something that's very, very high reliability. And so that was really kind of the paradigm at that point is, if we just keep pushing on this, eventually we'll be able to write programs or something like programs, plans that will solve interestingly complex problems. So go ahead to IROS 2015. I was giving a keynote. And of course, by now, deep learning had come in. There was starting to be rapid progress in being able to detect objects in images. And so in some sense, you could start to fill in a lot of the blanks in that program from 2000. But I pointed out there was still this kind of missing notion of generality and interactivity that you wanted to have. And so this is literally one of the last slides from that talk where I opined that eventually what we need to get to is we have to be able to interact with robots around the grounding that their tasks are embedded in. So this is just kind of a fake dialogue between, a robot, Iris, get the laundry from Sophia's room, and then Iris saying, I don't know what you mean, me doing a little bit of clarification, and eventually, essentially, the robot understanding what to do and going off to do it. And one of the key things I pointed out at the time is that really this is what we now know as in-context learning, meaning really I was kind of teaching the robot and expanding its knowledge by giving it answers, and it would be able to eventually solve these problems. But of course, this wasn't really there in 2015. This is just kind of what I was imagining. But lo and behold, about 2021, we actually wrote a paper where we were able to plug natural language in with a robot, and we could actually start to tell it things like pick up this block and put it down next to that block. And of course, the real advance here that made that possible was transformers and the fact that we could actually use language models, we could train them efficiently, we could ground them in a physical scene using images, and we could then combine that with some reinforcement learning that actually was trained in simulation, it was transferred to the real world, and we were able to compose a system that had a language channel, it had an RGBD channel, it had a motion channel, And suddenly this all started to work together. And like for the first time, I was actually starting to see, hey, we actually might be able to build something that is pretty close to that workshop assistant that I wanted, 20-ish years ago. But of course, we changed our paradigm to do that. So we went from things that were very explicit and composable and debuggable and testable to something that really is written in the language of mathematics and driven by data and computation. And it's very adaptable, it's capable, it's general, but it doesn't have a lot of the properties that we saw before. And so we kind of gave up on some things to gain something else. And of course, the epitome of this is your foundation models. The last two speakers have gotten to this same point of we're now at that ChatGPT plus moment, I guess, where we've seen the power of training on very large data sets. We've seen this notion of emergent capabilities. And so now the real question is, can we apply this to robotics, and what does it mean? And Dieter, I know, raised exactly the same question, and I think in many ways, he and I have a very similar view of where I think this is going to go. So the real question is, will general-purpose sensor-based robotics fall to brute force learning? And I want to emphasize the word brute force, because as we all know, what really makes these models work at this point is data at enormous scale, combined with computation at enormous scale, combined with some other kind of special tricks that make the recipe of modern AI work. So the first real question is data really the problem that we face? So there are a lot of folks who will say, well, the real challenge for robotics is just that we don't have data sets in the same way. We don't have every person on the face of the earth uploading motion data sets from their home robot combined with a caption and a picture so that we could actually train some huge model on that data. So that is certainly one of the challenges we face, is we don't have the same sort of data to train on. And if we really believe that brute force learning is the way to go, then certainly finding ways to capture that data is a path. But I spent the last 3 years before my current role working at Amazon. And in Amazon, I was actually trying to lead groups that were building and fielding vision-based systems that had to work in the real world. And one of the things that we found out, and this was actually brought up in a question earlier, is when you go to the real world, it's very tempting to solve a bunch of the problem. You launch your system, something doesn't happen the way you expected, and say, oh, that's an edge case. I need to figure out how to deal with that edge case. And so you deal with that edge case typically by massaging either the model or the code around it, but then the next edge case comes up, and then you got to solve that edge case. And what actually you find out is the edge case is the general case. The real world is really a long tail of unique events, many of which have never occurred before and may never occur again. And so if you really want to think about engineering systems that work in the real world, they have to be able to think and reason and deal with cases that have never before occurred and may never occur again. And these pictures illustrate some different examples, but actually I'll just point out the one on the left here just occurred to me the other day because I had my Tesla in auto drive mode for a while. And I came up to an intersection, it was about the time school started, and there was a crossing guard standing in the middle of the intersection. And I am pretty darn sure that my Tesla Autodrive does not know anything about stopping and waiting for a crossing guard who is, waving traffic and people in different directions and then moving on. And that's just one of the many tens or hundreds or thousands of edge cases that occur that you need essentially the human driver to take care of in order to ensure that the vehicle is safe. So I want to just close with 3 thoughts about how I think this is going to go and why it won't be brute force learning, but why I think robotics does have a really unique role to play in the world of learning. The first is kind of going back to the program. We've been trained, at least in computer science, you're trained to build systems that are perfection in some sense. You build code that works, you compose that code with other code that works, and you get systems that work. And I think even in robotics, we've learned to engineer systems so that the robot can work perfectly in the broader system, because that's what it takes to be practical in many real-world applications. But The fact is, as soon as you start to plug AI in the middle, robots will always be imperfect. And so we really need to learn to engineer around or with imperfection. We need to build systems that have the right sort of redundancy in them, that understand what failure is and can recognize failure and deal with it. And the last thing, and I bold-face this, is, and we have to kind of move beyond the idea that this is just an empirical endeavor, but there's actual theory to building reliable, redundant systems that I think is yet to be discovered. And I think it's going to be the thing that's going to make it possible to field robotics in many of the applications where currently it's still challenging to do so using AI. The second thing I'll say is, I actually also believe that this is not just an academic endeavor. I do believe industry has a key role. When I started working at Amazon and I started to see the reality of launching these systems, I really had a different lens on what are some of the important problems to solve. And also I saw that there was a lot of data that was available and a lot of compute that was available to think about solving them in a different way than I would have done in academia. And if anything, if you look at the last few years, you see that really, if we can find the right sort of synergy between the ability of basic research to advance new ideas, kind of getting beyond what we know today, combined with industry's ability to create, in some sense, living labs around these that we can study and start to learn from, we'll be able to operate in partnership much more effectively than if we say this is just an academic endeavor, or if industry is just trying to figure out how to launch things. And last but not least, I think that research really has to figure out, I would say robotics research, learning research in robotics, really has to learn to capitalize on the uniqueness of robotics. And the thing that I always said when we talked about robotics inside of Amazon is, what's unique about robotics is every interaction with the environment is an experiment. And that's completely different than what we see in machine learning today, where you're learning passively from data. And in fact, the big advance for ChatGPT was when you actually added an active interaction component with people. So I think robotics, we're in the same world. We really need to capitalize on the fact that we interact with the world. Those interactions are experiments. We have many correlated signals that we can exploit. We heard about haptics earlier. We know about vision. There's sound. There's the interaction with the human. Those are all signals that are a possible point or a possible source of learning. And I do think, and Dieter mentioned this as well, I think simulation actually plays a key role in this as well, as kind of the way to do experiments at scale before you do the real experiment in the real world. So let me just close by saying, that little kid that you saw in the first picture, he's graduated from high school, he graduated from college, he's actually finishing his PhD right now. I still don't have that robot assistant, but I feel like we've made a lot of progress, but I think there's still much more to make. Just as Dieter said, that last mile is often the hardest. So I'm really hoping, however, that many of you out there, the next generation, take up this challenge, because I think it really is an interesting challenge and something that will really shape our future in many ways. So with that, thank you.
Thank you, Greg. Great thoughts. Questions? Questions? I don't see any. So I will have one.
Okay.
So, Greg, when in your 3 thoughts at the end, what is, in your opinion, the way to go? I mean, concretely, if I get back to my lab tomorrow, what should I do so that I follow your advice, your path?
You want me to give you a concrete idea?
Yes.
So, if I were going back to the lab at this point, I'm just trying to think, the thing that we kept trying to work on was exactly this notion of how do you think about the interaction as a physical experiment. And so a lot of that is thinking about simulation as a way to both find the positive and the negative, kind of the choice point examples. And then basically choosing operations that are right on the boundary, because those are the ones that have maximum learning potential. And also, by prompting these systems in the right way, you can also start to find out what is the differentiating point. Like, for example, in simulation that causes the simulation to go in one direction or the other, and see if that differentiating point actually shows up in the real world. So it's a way of actually backing out of the model. What are the physical differences that actually, for example, make it possible to pick something up versus not pick something up? And that's what I'd be doing if I were back in the lab right now.
Okay, we'll follow suit.
Right.
Thank you
Thank
very
you.
much.